All right. So there we go. So one thing I want to mention before we get going. So I got a couple emails that people were having trouble accessing quiz 3 last night. I'm not really sure why, because people still accessed it after the fact. So I'm not sure if it was just like you weren't sure of how it was showing up. I think it a little bit different than the other quizzes. For some reason, defaulted the grade to 0. I might have accidentally clicked on something when I was hitting submit so that it did that, and I didn't realize it. So if there's any confusion in that, people were adequate that they couldn't access it. So I posted what looked like an additional quiz and called it quiz 3 alternate quiz. Or alternate, what did I call it? Alternate version. Am I in the right class here? Yeah. Yeah. So the grade book's a little messed up right now because if you didn't do one of them, but you did the other, like you only had to do one, right? And so I'll kind of get those meshed together. So I mentioned a couple things. First of all, I saw some of you then take this one after you'd already taken the first. So what score do you think I'm going to take? Your first one. A couple of you tried to game the system and also did both of them after I posted it. So which one do you think I'm going to take? The one that was submitted first, right? So I'll kind of get those molded into one column. I don't know if I'll get it done this afternoon. If not, for sure tomorrow, you'll kind of see that happen. So like I said, I'm not sure. I only had a couple people reach out that they couldn't, but they were adamant that they couldn't access the quiz. So that's why I created this additional kind of version of it. But it looks like everyone was able to get at least one of them working. And based off of the emails I got back, that I think everyone was able to get one working. So those quizzes are going to be good review, as well as the practice problem that go along with them for the exam. I also mentioned I posted that practice exam. So we're really kind of focused on some of those a little bit more on Tuesday. Today, I'm going to kind of go through similar types of questions or give you the types of material you might be expected to know on the exam. We're going to work through an additional couple data sets, which I have in that multiple linear regression week 7-5. Right? So I'll kind of walk through this slow. I think it'll help not only with the exam, but also that third problem set, right? Which is due when? So let's scroll up here, right? Have that kind of set to be due by the time we meet in class on Tuesday. So you got a little more time to work on that. Going to get that done. Office hours next Monday if you want to stop by for last minute questions. I might be around a little bit tomorrow. If you send me an email, we can maybe schedule a time. I've got some meetings and things that we have to work around, but I should be around a decent majority of the day tomorrow as well, from like 8 to 3. What else do I have to say? I think that's it. So where we left off was kind of, I had introduced this idea of joint hypothesis testing. I wanted to clarify a little bit because I did have a question on it. I showed you last class the way that you can kind of use that residual sum of squares from both a restricted model where you're not including certain variables, and then also the unrestricted model where you include these multiple variables that you want to test the joint significance of. You can kind of think about joint significance. Another term could be simultaneous significance. That might be a better joint significance is what you'll see in every textbook. I like simultaneous significance. I think that kind of makes sense. But we can also use a version of this F statistic, or we can calculate it using the R squared values. So I'll actually show you an example of this today. And there, I think it makes a little bit more sense, or it's a little bit easier to talk about. So if I run this unrestricted model, so let's say I run a regression where I only have like one variable on the right-hand side, I then include 3 additional variables. So that new model with all of the variables would be my unrestricted model. What has to happen to the R squared? Has to be, if I add more variables to my right-hand side, what's going to happen to the proportion of the variation I can explain in my dependent y variable? Has to go up. So what's this sign always going to be? The unrestricted model will always have a higher R squared, so that's positive. The number of restrictions, well, I can't have negative number of restrictions, or it has to be 0 would be the lowest possible. And then here, 1 minus an R squared, well, this is always going to be a positive value, right? The highest this could ever be is technically 1. In fact, it can't ever truly be 1. That would mean we have every single thing, right? A measurement on every single thing that matters. That's just statistically improbable, right? I mean, to have every single thing, right? And then all these will be kind of positive values as well. So we should have this F statistic is really telling us like how much more of the variation can we explain? This mode was kind of like, how much less of the variation is unexplained. It's just two different ways of saying the same thing. I think most people probably argue this one makes a little bit more sense, like intuitive sense. Right? So you're always going to have these R-squared values if I ask you to calculate an F statistic or think about doing joint significance testing. So I'll kind of use this from here on out today. Okay. So let's just pull open this data file. And I think I changed my global, so hopefully it's working correctly today. Scroll down here. We're going to use this star public use one. Okay. There you go. So I had kind of this initial idea, and we'll kind of work through some different topics. So there's a variable in this data set called dad2, mom2. This just is a dummy variable for whether or not the person's parent went to college. So we're going to end up looking at someone's GPA as a freshman in college and some of the things that might help predict that. If I'm an admissions department, this is maybe something I'd want to do. Also, before I forget, on that third problem set, someone asked me at the beginning of class, I forgot to rename one of the variables. I referenced it as total rooms. The variable rooms is total rooms. Right? So if you had any confusion there, rooms is total rooms. I meant to rename it before I posted that actual data file. It didn't quite line up with what I was referencing in the problem set. I think probably could kind of figure that out based off the variables that existed. But I just wanted to mention that before we get too far into this. So I'm going to have kind of these indicators for whether or not the person's parent went to college. So I don't want to run this line of code. I had it in there for a reason. So I'll kind of show you what ends up happening. If I were only to keep the observations that wasn't missing college, actually, no, I might have done this for a reason. Let's look at the actual data. Here we go. So we'll go to in search. Let's look for this mom2 variable. So we've got ones and zeros. So it doesn't look like I have any missing data here. So I remember why I put this in here. Right? So if we're doing joint hypothesis testing, we can run into one issue. So I'm going to leave this here for now. We'll kind of revisit why I might need a line of code like this in practice if I'm doing joint hypothesis testing. But for now, we're going to skip this. Okay. So in fact, just to make sure, I'm going to turn it into a comment for right now. Okay? So I'm going to rename this other variable. So did I already do this? I'm talking on. Okay, I didn't rename these. So I'm going to rename these college variables. I'm also going to rename this GPA 0, which is basically just what their GPA was coming into college or their high school GPA. So what I'm going to try to do is predict their GPA in year one or their freshman year GPA just based on their age, whether or not they were female, and their high school GPA. Okay. So when I threw in this kind of comment of robust, why, when I did that, what did that adjust for? Do you remember what we've talked about where in Stata I'd want to include this robust command? So let's see what happens. If I run it without this robust command, okay, what might I be concerned with? Right? Well, let's look at, and I'm not sure if this is the case. I'm kind of doing some of this on the fly because I know what's on the exam, so I know what topics you should know. So I kind of have some of this code ahead of time. Oh, did someone unplug this? God damn it. Let's hope this is the right one. All right, there we go. Okay, so if I'm trying to predict kind of GPAs from year one, or kind of think about this as like their freshman GPA, and I had age, I had, what were the other ones? High school GPA, forgot the G here, and then whether or not they were female, this dummy variable, right? So what might be kind of an issue if I'm thinking about the relationship here maybe of age and GPA as a freshman, right? So what's the majority of my data going to look like? when you're a freshman, what are the majority of ages I'm going to see? 18, and depending on the semester, maybe 19. So I'm going to have a lot of data points with GPAs that vary quite a bit here. Now, what could be the case is if I start to see people in their freshman year that are out here at 20, 21, they're starting college later, what would you stereotypically maybe assume that coming out of high school they didn't have as high of? So maybe they went to like a community college because initially, what would their GPA in high school not have been high enough to do? To make it in, right? So we might think about here, it's likely I'm going to see groups of individuals who had at higher ages relatively like lower aptitude. So maybe when I look at their freshman GPAs, maybe they're lower, and not only are they lower, they're kind of more tightly knit. Now, you could probably also tell a story where maybe these are people who came from different socioeconomic backgrounds, right? So maybe their transcripts didn't look as good coming out of high school, but once they went to like a community college, they were really smart. So maybe when I'm looking at some of these people, maybe some of them were not as good as students, and so they had to kind of take a longer route, but maybe some of them were like really good. So maybe I saw an even wider range here. So the fact that there's different variation, so even if it was the alternate one with the red, if there's different variation in that y variable for different values of this x variable, what did we say that that was? Starts with an H. So my errors for this x value would be heteroscedastic, right? That the variation of my error term for these different ages is going to be different. Now, this one isn't quite as clear. I would likely tell you that, right, why this heteroscedasticity might exist, but this is an example where possibly it did. Right? So anytime we had this heteroscedasticity, we said it's going to mess with our standard errors. Right? More often than not, it's actually going to cause them to be a little bit too small. Right? So if my standard errors are too small, if I'm looking at that age coefficient, what's going to happen if my standard errors are a little bit too small? What's it going to do to my test statistic? Increase it, which is going to do what to my p-value? Decrease it. I would know how to do these things, by the way. I might ask you a question, wink, wink, like if there's heteroscedasticity in the error terms, which of the following are true? The test statistic will be larger, the p-value will be small. I'll give you these different options. And if the p-value is smaller, I'm going to be more likely to be able to reject that null hypothesis from my linear regression, which my null hypothesis is always what for a coefficient? We got to know this going into the exam, otherwise it's going to be an absolute bloodbath. I always start out assuming my coefficient is equal to 0. There's no effect, right? Yeah.
So when you get heteroscedasticity, your standard error decreases.
So if I don't account for the heteroscedasticity that exists, my standard errors might look like they're too small, okay, right? Once I adjust for it, what happens? Standard errors go up, test statistic goes down, p-value goes up. Now I'm less likely. So we want to adjust for this heteroscedasticity. So we'll kind of look at what this, or kind of see what this looks like with our example here. So I've got my age variable, and maybe there isn't. Maybe it doesn't change my, I'm just assuming maybe there is here. So here I've got a pretty low p-value, right? If I instead run this robust command and account for that heteroscedasticity, now it doesn't do it by much, but my kind of assumption must have been somewhat true. Why? Because when I didn't adjust for that heteroscedasticity, what happened? My p-value was a little bit lower than what it should have been, which made it more likely I could reject the null. Once I adjust for this heteroscedasticity, what happened to that standard error on my age variable? It went not up by much, but it went up a little bit, right? Which if the standard error goes up, that's going to drive, standard error went up, it's going to drive our test statistic down, it's going to drive our p-value up, making it less likely. Okay. So we can kind of see all these things. So the test statistic was what? Negative 3.38 before, now it's only negative 3.08. Okay. So that robust command controls for, or essentially adjusts for the fact that we might have had our standard errors being screwed up by this heteroscedasticity in some of our variables. Now, not only did it adjust for age, it actually adjusts for heteroscedasticity in any one of those variables, right? So if I'm looking at this, and I'm looking at the kind of high school, well, yeah, I'll punt on that. We'll kind of stay there with the age variable, right? So I wanted to revisit that idea of heteroscedasticity and that we might want to account for that, okay? Whoa. So if we do that, right, the next thing that I might want to think about is, okay, this is kind of more recent, right, what we talked about. Let's say I'm interested in whether or not the parents going to college is going to be able to explain any more of the variation in a freshman's GPA. So I include those variables, college mom, college dad, whether or not the father and mother went to college. Okay? Excuse me. So here I kind of have, and I didn't do this last class, but we can kind of do this joint significance test by already adjusting for, in both regressions, the heteroscedasticity. It's a hard word to say. Heteroscedasticity that already might exist. So notice I've used the robust commands in both regressions here, okay? So I'll just run this again just so we kind of have them back to back, okay? So here was the original one. Looks like what percent of the variation were we explaining? Just over 20%. If I then come down here, what amount of the variation can we explain here? Actually looks like it went down, right? So this is kind of a weird one. But what's going on? What's also different in these two regressions? Pointing to it, my number of observations. So I didn't mention this last class, but inherently, when I'm doing this joint significance test, what I'm assuming is that it's being done for the exact same sample. When can this be violated? Well, let's say I go to the data, and I was trying to scroll through it earlier to kind of see, because there should be some somewhere where, oh, actually, let's sort the data so I can show it to you without scrolling. So let's go all the way down here. Oh, there's some observations where that college mom variable is just missing. So when I didn't use that variable, Stata was using these observations because there wasn't any missing data. But as soon as I include these new additional controls, if there's missing values, what will Stata do? Just drops those observations. We can only run a regression if we have data on that observation for every single variable that we've included on the right-hand side. So when we're doing this joint hypothesis testing, we need to be a little bit careful, which is why up here, oops, I had this keep command. Because I want to make sure once I get to doing that joint hypothesis testing that I have the exact same sample, or I'm only using the observations that had data for every variable I'm going to use. So what was the variables that were kind of giving me issues? Well, these college ones. So I only want to keep the observations if I'm not missing that college dad variable, and I'm not missing that mom college one, whatever, college mom variable. Okay? So what this will do, we go back here. What should happen is I now end up with just this sample where it was only the observations where I had information on if the parents went to college. So I should have a new sample size of 1,401 here. Right? So go ahead, kind of run this. Only keep the observations where I had non-missing data. Now I'll go back down here. Now, hopefully, what I'm telling you is true. What should happen to my F statistic when I include these additional variables? Or F statistic, my R squared, when I include these additional variables, it should go up, right? And I should have a positive F statistic. So sure enough, now I've got, okay, same sample size. That's a good indicator. I'm using, got the same data set, the same observations now. What happened to my R squared? Well, it's now 0.1956 to 0.1974. So it did go up a little bit by including these additional variables. Not much. So before I even do this test, if you had to guess, do we think that these two variables being included are going to be jointly significant? If I'm just looking at the difference in the R squared, it's pretty small. However, even a small difference, if I find that from a really large data set, that could still end up with statistical significance. Right? So this is the idea that Y, well, just like any statistic, right? we kind of said, pull this open too while I'm thinking about it. I'm going to open up this formula sheet for us. Oh, there we go. So my standard error here, right? I'll kind of use this equation. So to rewrite my test statistic, so I'd have my coefficient divided by my standard error, which we had there was the sum of the differences between y, that's my predicted y, squared over n minus 1, right? So kind of the idea that when we're creating that F statistic, it's the difference in the R squared. The same thing I'm going to do with just a regular test statistic will apply. It's just a little bit easier to see it here first, and then we'll think about with the F statistic the same thing. So if I find a really small coefficient, so like let's say I find a sample coefficient that's like 0.001. Okay, well that's not a very large effect, but it could still be statistically significant, right? Because it's not zero, right? It's not far from zero, but if my sample size is high, what's going to happen to this denominator, which represents my standard error? The higher our sample size, what's happening to our standard errors? They're getting smaller, right? You can kind of think about what we just have more, like seeing the same coefficient, but from a larger data set is more meaningful. If I see it from only 10 people, it could have some just really odd observations in my sample there. Seeing it from 10,000 people, well, even if I have the outliers, they're not going to influence my results by very much. So that standard error goes down. What's going to happen to my test statistic? It's going to go up, which means my p-value is going to go down. And having these large sample sizes makes it more likely I can reject. So the same thing is going to take place for our F statistic. So this was what our R squared from the unrestricted model minus restricted over Q, 1 minus R squared from the restricted over N minus K minus 1. So just a kind of reminder of what these things are, because I could ask you to calculate that F statistic by hand. I'll show you how you do it in Stata, but I'll also, just using the regression output we've only looked at, I could actually calculate it. Calculate this by hand. I'm getting a little excited here, okay? So what was my original R squared? And this is where I'm going to pull this open so I can get these numbers without switching back and forth. From the restricted model, where we didn't include the parent college variables, this was 0.1956. And then after we included those college variables for the parents, 0.1974. So it didn't go up by much, just like we might not see a very large coefficient. However, if we were doing this and the sample size is relatively large, what's going to end up happening to this denominator? In a weird way, this denominator, this is by all means also a completely incorrect way to say this, but just to make it easier to kind of see the similarities, it's kind of like the standard error of that change in my R squared, right? That is by all means not really what it represents, but it's somewhat synonymous to that. So what would having a higher sample size do? It's going to drive down that standard error, which is going to then do what to my F statistic? Make it larger, and then the same implications occur. That would make my p-value smaller and make it more likely, seeing that same difference, I could actually make a rejection of this joint significance. Is that any questions on anything I've said there before we keep on moving? So just as a reminder, what was Q? We remember? Yeah, so one way to remember that is when I'm looking at the difference in the R squared from the restricted and unrestricted model, Q is the number of variables that I added into the unrestricted model. So for us, this was just 2. All right, we added 2. I could do joint hypothesis testing for 3, 4, 5, however many variables I want to. What was K? So this was our total number of variables, and here we want to be careful in the unrestricted model. So we had the 2 parent college variables, high school GPA, age, and female. So RK would be 5. And then I think our sample size was 1401. We now have all the values. We could go ahead and calculate what this F statistic is. So I might ask you to calculate an F statistic on the exam. If I do, you can use this version of the formula where you use the R squared, not those residual sum of squares. Okay. And there really, I don't think this part's going to be hard. If I give you the output, I think you can figure out where the R squared values are. Knowing what Q represents, the number of restrictions, and maybe I'll give you an example where maybe I don't use 2 always, maybe it is 3, and then K, the number of variables that are in that unrestricted model. Okay. So I can almost guarantee you that you'll see a question like that in the exam because I have it written. Okay. Any questions on this before we keep moving here? And just to kind of, yeah. Yep. So think about it this way. If I have a restricted model, am I going to have more variables or fewer variables? If I restrict something, there's going to be fewer. So my model where I don't include those parent college variables, that's my restricted model. There's my R squared from that model. What's the R squared from the model that's unrestricted, where I include those variables? Right here, right? That's where I'm getting those values. Yep. So I would do something similar to this, where I give you like 2 regression outputs. One of them has, they have the same variables initially, but then in one of them, I include some additional variables or have restrictions there. Any questions on that before we keep moving here? Okay, so I could go ahead and do that. Problem is if I do it that way, so I might ask you to calculate an F statistic. I'm not going to ask you to I'm not going to give you this and then ask you to tell me if it's statistically significant. If I asked you about the statistical significance for like joint significance tests, I would give you output that looks like this. Right? I would give you run this test command where we said, if I run this regression, the full unrestricted regression, I then use the test command. That's going to do my joint significance test for me. It's going to calculate that F statistic. So if you want to go ahead and plug all those values in, you should get something that's roughly around 1.58. There might be like some rounding issues because like we were taking the R squared to the 4th decimal. This is taking the R squared out to like, I don't even remember where Stata stops, like really far out. So we might have a slight discrepancy if you calculate plugging those numbers in, doing it by hand with what Stata would tell us. But within like the 2nd decimal, it would be the same value. Okay. And I would never ask you a question like obviously where that's going to, I either ask you to calculate the F statistic using those values, which inherently incorporates the rounding, or I'll give you the output like this, and there I'm not going to ask you for the F statistic. What might I do here? Ask you whether or not those variables are jointly significant. So just like with coefficient estimates, what do we start out assuming? That these 2 variables have what kind of an effect? We always start out assuming there is no effect, right? So can I say that these 2 variables were able to increase my R squared essentially, or explain more of the variation in freshman year GPAs? Well, at my conventional levels, what levels could I say that these are statistically significant or that they did explain some more of the variation? P-value here on my test. So this probability of seeing the test statistic or anything greater, we said, actually, this isn't even a 2-tailed test because we know the R squared has to go up. It's always a right-tailed test. So here we're only looking at 1 tail. This is essentially representing my p-value. So can I say that this has any statistical significance adding these to my model? Not less than 0.1, 0.05, or 0.01. Right? I can't say at any level that this does. Okay. So once again, just like with coefficient estimates, we're just comparing, is that p-value less than these 3 benchmark alphas we always use? Okay. Any questions on anything there? Because I can also guarantee you, I'm going to give you some output from this test command and ask you.
So, like when you're looking at the output regression, where is n minus k minus 1 on regression?
Nowhere.
Nowhere. Okay. So it's not.
Where's n?
It's not going to be degrees of freedom 2 or whatever it is. It's like degrees of freedom 1, degrees of freedom 2, like just a regular regression.
Like right here?
No, like can you scroll up a little more?
You mean if I don't use the robust command?
Yeah, if you don't.
It's going to be the same thing.
1400, is that N minus K minus?
So it should always be N minus K minus 1 here.
Okay.
This will not represent Q though. What was our Q?
What is the conversion?
What was our number of restrictions?
2.
Yeah, so this is something slightly different. This is not a joint significance test. It will happen that this will always coincide with N minus K minus 1 for the unrestricted model. Notice if I do the same thing, but for the restricted model, so just in case, I wouldn't use that. I would think more through, because notice here, what is it now? Oh, it's not taking into consideration. So I can kind of screw myself up a little bit if I'm trying to use that from the regression output. I would kind of, since you have that formula sheet and it's got N minus K minus 1 in here, it's a lot easier to think about how many variables did I include, that's K. And then from the regression output, whether or not I give you a robust command included or not. So that's another reason why I'm glad you asked this question. If we're using the robust command, that limits a little bit of what we're seeing from Stata, right? In which case, if I gave you that output, you can't, I shouldn't say cheat, right? Actually, oh, it does give it that. Never mind. That gives it to us as well, right? So you could actually grab from there. I just don't want you to like get confused where if you're looking at these two, right, that number is not the same between both of them. So it's probably easier to think about that formula and okay, N is the number of observations. K, I'm just looking at the number of variables I included and just compute that number so you don't get confused there.
So in that regression, K would be 5.
Yep, because if we think about how many total variables did we include in that unrestricted model? 1, 2, 3, 4, 5. K is the number of independent variables, so you don't include the constant there. Yep. Yeah, that F statistic is for something a little bit different, which we're not going to cover, so don't worry about it. Okay. Any other questions on this before we keep moving? Okay with this? Okay. Yeah, this is just different numbers. We could do the same thing. I want to do something a little bit different. So I want to cover some older stuff. So let's go here. I'm going to change this to be my global. And I have this powerlifting in class data set that should be always worried about, yeah, should be kind of up there on Canvas for us. So I'm going to just open that data set up, maybe. Did I not drag and drop it in? Let's see. I must have misspelled something. All right, now we've got it opened up. Did I misspell? I used this earlier. Oh. Oh. What did I forget? I need the use command. Now it should work. There we go. All right. So I've got this powerlifting in class data file opened up. And I've got some different stuff going on with it. So the first thing is, if you're not familiar with powerlifting, that doesn't matter. But there is different divisions, right? So here, I kind of had, I'm going to create this additional third category. So it's where they can use like all this crazy like elastic gear so they can lift more weight. We're just going to generate this new variable so we can kind of include some multiple dummy variables here in a second. Okay. So the first thing that we're going to do is just run a very naive regression. So when you get to the exam, this is going to go all the way back to like basic linear regression where we just have one variable on the right-hand side. Now, you might have a couple questions over like sample mean stuff, but it's not going to be a lot. And the bulk majority of this exam is going to be about linear regression. Okay. So if I run this regression, what do you think is likely true about the sign on that body weight? So what I'm trying to do here is predict the total amount of weight lifted in kilograms based off of someone's body weight. You think someone who's 400 pounds is going to be able to lift more weight than someone who's 100? Probably. So you probably would expect that coefficient is going to be positive. So I run this. Sure enough, it looks like it's positive, right? Is it statistically significant? At every single level, right? Very low p-value. So what might be going on here? So stereotypically, but also not really stereotypically, this is just a byproduct of biology. What's going to be true about every male, the average male in my data set relative to the average female? In terms of their body weight, they're going to be heavier on average. Also, we have hormone differences. It's likely there's going to be differences in strength. So I've got this kind of omitted variable, which is whether or not the individual is male or not, which is going to be correlated with body weight. And it's also going to be correlated with how much weight is lifted. So what issue am I going to have? If I run this naive regression, I've got an omitted variable bias. So I could ask you a couple things. So one question that you might see on the exam is just, all right, I don't remember the name of the variable, but weight lifted in kilograms. And then we had kind of body weight in kilograms. If I leave out this important omitted variable that should be included, which is whether or not this lifter was male, just a dummy variable, what would our bias be? So I'll show you where it's at in the formula sheet in a second, but I have that formula on the formula sheet. The estimate you'll see, if you have an important omitted variable bias, you'll see that coefficient estimate will be the true effect plus the effect of that omitted variable times the covariance of the variable you included in your regression and that omitted variable divided by the variance of the variable you did include. So for us, this is going to be what? This is our bias. So here we're thinking about what would the coefficient on that omitted variable be times the covariance between kind of body weight and kilograms, just abbreviating things here for the sake of time, and the variable we excluded or omitted divided by the variance of that variable we included. Okay? So an example like this, and I might even give you some like hints. I'm trying to use examples like this where I think it's very obvious, or I would leave it short answer, in which case I guess if you told me you thought that males on average weigh less, I would grade it accordingly, and I wouldn't, I'm not testing you about your knowledge on male body weight or female body weight, but you would need to tell me something about, if you have an omitted variable bias, what matters? The covariance of the variable you included and the omitted variable. Here, it's likely we could say this is positive. I can't think of any reason why it wouldn't be, and we could actually take a look at the data here in a second and see it is positive. Also, based off of my limited knowledge about hormones, right, I would expect that the individual being male, what's that effect would that have if I included that variable in my regression on the weight that they lifted? I would expect that's positive as well. Once again, if you told me you're more of an expert than me, and you told me you think testosterone is going to lower the overall muscle mass and strength of the individual, I'll take your word for it, right? I'm not testing you on that. Just you have to tell me what you think that sign of the effect of that omitted variable is. Does that make sense what I'm getting at there? So I'm going to ask you a question like this. Also, you're here in class and I'd write some of this down. I'm telling you when I say I'm going to do this, I'm going to do this, right? So I might give you something like this and say, what's the sign of the omitted variable and why? You need to know that the sign of that omitted variable depends on these two things. Why? Because the variance will always be positive, right? So here, it's likely that, yeah, I'm seeing a positive estimate, but what might that body weight coefficient be picking up a lot of the effect of? The individual being male. So as soon as I include that male variable, what happens to my estimate? That bias is completely eliminated, okay? So let's take a look and see what happens as soon as I include just that one additional male variable, right? Well, sure enough, I went from 5 to 3, so not quite in half, but it cut my estimate almost in half, right? So it must have been that there was a pretty large positive bias there. Now, what's another way? Yeah.
So when it's a positive bias not included, when you included a as a negative effect on coefficient, it decreases it.
That I wouldn't quite phrase it that way. It will decrease it. Why? Because when you include that variable, it eliminates a positive bias. So you can think about it this way. What were we finding here? This effect was like 3. We were seeing 5 because this bias must have been equal to 2. So as soon as I include that variable, I've eliminated this bias. So now the estimate I see will not be 3 plus 2. It'll only be 3. Okay. Go here and then over here. No.
The omitted variable bias that we just looked over, you said it's kind of on the issue. You're talking about whether, you know, now and whether like the body weight or
No. So the general thing that you care about, so just not to make it specific to this example, the variance is always positive. So what 2 things could the sign be different on? The covariance, I'll write this out in a general context. So X1, what are X1 and X2 really representing here? So this is going to be beta 2 would have been what was the effect of the omitted variable if it had been included in the regression. So that could be positive or negative, right? I don't know. That's what I would kind of have to think about or look into the data a little bit further. And then the other thing that mattered, we said, well, the variance doesn't matter because it's always positive. So what else matters? The covariance of the variable that you included, that you're looking at the coefficient estimate of, and that omitted variable. Right? So thinking about what X1 and X2 represent here, what body weight and male represented, it was the variable that I was including, that I was looking at the estimate of, and then its covariance with the omitted variable. Is that what you were asking? Yep.
So this omitted bias over estimates the coefficient.
Yep. Yep. Any other questions on this before we keep moving here? So what's another thing that I could do? If I gave you what this effect was, and then I gave you some data output where I show you the covariance matrix, well, that covariance matrix would tell you the covariance and the variance. So maybe I do something like this. I work backwards. May not be as likely to do this, but just I think it'll help solidify this. So let's say I ran this regression. I then also gave you the covariance matrix between the variable you included, your independent variable of body weight, and then that omitted variable, right? So let's say I gave you this output. So here, I don't have the omitted variable, right? But I'm giving you the covariance matrix and what the effect of that variable was if it had been included. Excuse me. So here, if I asked you, what would the coefficient estimate be if you ran this regression without male? How would you do that? So if we look at our formula, so I'll show you where this is at in the formula sheet. I can find it. Should I scroll down? I know it's on here.
It's right there.
Oh, yeah, right here. So here's my estimate that I'll see if I excluded that variable. So I gave you the output where that variable is included. So you know what the true effect of beta 1 is, or you know the true effect of body weight. That's going to be approximately 3. So I could plug that in to my formula. The coefficient estimate of the variable that I omitted, if I asked you, what would the bias be if you did omit it? Well, the effect of male on your dependent variable of weight lifted would be about around 200 or 198.66. So I could plug that in here. What is the covariance? Well, my covariance matrix tells me the relationship between body weight and male, 5.44. And then the cross, this is just going to represent what's the covariance of male with male? That's just my variance. So I've got the variance of the variable I included body weight the covariance of the omitted variable. So if I plugged in the covariance, plugged in the variance, I'm giving you what the effective male would have been. You can tell me the estimate that you would have seen because you know that it would be 3 plus, what was it? 3 plus 200 times 5 divided by 541. Right? So you could work in either direction. I could give you the regression output where the variable is omitted and ask you what the bias would be. Or I could give you the regression output where you've included that variable and said, if you did omit it, what estimate would you have seen on body weight? Right? If you did omit male, what estimate would you have seen? You're just grabbing the exact same piece of information. You've just got something else that's missing there. Yeah. Yep. Yeah, it'll be included in your exam. Yep. Mm-hmm.
Where you might ask, like, if you had to solve this, what figure using data, like, what kind of.
Will it? No, I said last class. I'm not going to ask you any coding questions. The extent to which you need to know stata is you need to know how to be able to interpret the output. Now, there's one exception of that. I might give you kind of something like this and expect you know how to write out what that actual regression is. That the first variable is your y variable, and here's the two variables that you included. But that's about the extent to which I'll expect you know that coding. Or, kind of to our earlier example, I'm not going to tell you exactly what the test command is. I'm going to hope that by the time we've had all this discussion, where is it? That if I tell you something about I'm doing joint hypothesis testing and I give you this output, you should know how to read that output in terms of a joint hypothesis test. Does that make sense? Answer your question? Okay. All right. Any other questions before we keep moving here?
The big response, like read right out. What is the big response?
It could be, right? So sometimes I wonder what so like here. Well, I'll show you the answers just to kind of look at it. These are, I don't write these for the fun of it. These are the types of questions and in the style that I would ask them on the exam. So, there might be multiple choice questions. There might also be interpret beta 1, right? So if I give you a regression, I mean, I'm not expecting, these aren't going to be the exact questions I ask, but I'm giving you a regression. I'm giving you some output. I then ask you to interpret what that coefficient is. So we're not doing as much of that here in class. I guess if I really wanted to kind of reiterate that, if I'm looking at my output here, how would I interpret, and here I'm kind of thinking about the order in which I wrote them. Here would be beta 1 would be with this variable beta 2 here. How would I interpret beta 1 or the coefficient on body weight here? So you definitely are going to have to make interpretations of variables, right? Coefficients. So how would I do that? It's going to be a 1 what increase in my independent variable? 1 unit or 1 kilogram, right? So I will give you the units of the variable. So okay, the way I interpret this coefficient is a 1 unit increase in X, so 1 additional kilogram of body weight would predict that the total amount lifted in weight goes up by what? 3 kilograms, right? So every pound heavier the person is, we would expect they can lift on average, or kilogram, we would expect that they lift on average 3 kilograms more. Now, I left something off here. What else do I need to throw into my interpretation if this is the output I gave you? Holding all else constant. Here, what am I holding constant? Whether or not they're male. Now, I could also think about here, how would I interpret beta 2 or the coefficient on male? So male is not a continuous variable. It's what we call a dummy or indicator variable. So what is the unit increase? How do I interpret that? So not quite, where you're thinking about a dependent variable that's a dummy variable, right? So remember, I always start out with a change in my X variable. So what's the 1 unit change here? if they're male relative to not, or the 1 group relative to the 0 group. So if the individual is male relative to female, the expected increase in the number of kilograms lifted would be about 200 kilograms higher. Okay. Holding what constant? So if I have a multiple linear regression, when I interpret a coefficient, it's holding all else constant. So here that would just be holding body weight constant. So male, female, the thought experiment, same body weight. One of them's male, one of them's not. The male would on average lift 200 kilograms more. Okay. Any other questions on that? Now, it's like, oh, well, you're telling me that all men are so strong. Well, what's likely also going to be correlated with the male variable that I haven't included here that might matter? Not body weight, but height, right? So there's likely still a lot of omitted variables that are still influencing these estimates that I haven't included yet. It's a very simple regression. So let's take these results with a grain of salt, right? But that's how we can interpret these coefficients. And I will definitely ask you to do that, right? Maybe more than once, probably definitely more than once, right? So be very comfortable making these interpretations of these coefficients. To your question, because you brought it up, and I think it's important, I don't think I have an example in here. Let's say instead, let me look at this. What variable could I use here? Okay, so I have this variable that we created, which was multiply, and it was just a 1-0 variable. So this was the division that they could use this like assistive equipment, right? So let's say I kind of do the reverse. It'd be kind of a weird regression. And I'm going to write this in terms of state in a second. But let's say I'm trying to predict whether or not it was a multiply competition where they could use this assistive device. And I have how much weight was lifted, whether or not they were male, and I just want to use those two. Well, I'm doing this in stata. So instead of this is my regression, I'm really running a regression like this, where my y variable is whether or not this competition, like the observation I have, came from one of these multiply lifts, competitions. And I'm trying to predict that based off of how much weight they lifted, right? Well, if these are assistive devices, when I see that they lifted more weight, it's likely a good indicator that they were part of this other division where they could use assistive devices, right? But to your point, when we make these interpretations, if my dependent variable is a 1 or a 0, when I run this regression, how would I interpret the coefficient on total kilograms lifted? So if the total weight lifted by this lifter in kilograms goes up by 1 unit or 1 kilogram, the change in the probability that they were part of one of these multiply kind of competitions would go up by what? 0.0009. So if I ask you for what percent, what was that percentage increase? Here it's always probability when we have a 1-0 dependent variable. So what would the percentage be? 0.09% increase, right? We can just scale that coefficient to a percentage by simply multiplying it by 100, okay? So I might do something like that on the exam, where I ask you how much, what's the predicted or what's the percentage change in some variable that's a dependent variable that's a 1-0. And then you'll look at that coefficient and you say, okay, that's the change in the probability. So what would the change in the percentage be? Just that, move the decimal 2 places. Or what if I asked you, here's another example. Let's say the person I'm telling you lifted 100 more kilograms. Actually, no, not 100. Let's do 50, right? So 50 more kilograms. What's the percentage change in the probability they belong to one of these multiply lifts or multiply meets? Sorry. Well, if that's the effect of 1 more kilogram lifted, how do I get the effect of 50? Simply multiply by 50, right? This is a simple linear regression equation. This is all, if I'm thinking about what I'm doing, once I have these coefficient estimates, I plug those numbers in. I'm just kind of thinking about a simple, so if this goes up by 50, how much does my y variable, it's just back to almost like, I don't even know what level of high school math, right? I have y as a function of x. If x goes up by 50, how much will y go up by? 50 times whatever that slope is, right? And these slopes we're getting from the regression output, okay? So here, what would the effect of 50 additional kilograms lifted be on the percent likelihood that this is one of these multiplied medians? Well, 0.009 times 50 be about what? 0.045-ish, right? So that would be the increase in the probability it was this multiplied meet. So what would it change in the percent be? 0.045 is just 4.5% increase. Okay. Any questions on that before we keep moving here? Okay. All right. Let me think if there's anything else I want to point out here. Let's go back here. Now I'm going to kind of run. We already did some of this stuff today. There's some other stuff I know on the exam that I think might matter. So let's say, we'll do some of this stuff next class. I think it'll be worthwhile. But let's say I kind of run this regression. And I've included a couple additional controls now. So I'm back to kind of predicting the total weight lifted by body weight, male. Now I'm including their age and kind of this was just like if there was absolutely no assistive devices allowed. Okay. So just kind of thinking about this to make the point here. Well, damn. It's not what I want. Maybe I'm going to scroll down here. Let me see if there's anything else in here I can use. Probably should have used the regression or the data we were using earlier. I'll mention this. This isn't like a perfect example, but I'll kind of mention what it would look like if it was a better example for the exam. Let's say I left out, these three columns. And I asked you which of the following variables at the 95% level can you say have a statistically significant effect on this dependent variable of total weight lifted? So you don't have the p-value, you don't have the test statistic, you don't have the standard errors. What are you going to have to use to determine whether or not I can reject the null? So I could probably back out kind of the standard error using the confidence interval and then calculate my test statistic, find my p-value. An easier way, if I ask you about the 95% confidence level, if I reject the null, what value can't be in my confidence interval? 0. So if I didn't give you these three columns and I just gave you these and asked you which variables can you say had a statistically significant effect on the y variable, what are you essentially looking for? I might write this down. You're looking for the confidence intervals that don't include 0. Those are the ones where you could reject the null at the 95% level. If they do include 0, well, there I know I'm going to fail to reject, and I can't say they have a statistically significant effect. So you can use the confidence intervals, and really it should line up with exactly the same decision you would make if you were using that p-value. So I might do that on one problem. I might leave out the p-values and the test statistic and everything. I could even leave out the coefficient and just ask you, is it statistically significant just using that confidence interval, right? So if it includes 0, you can't reject, so you can't say that it's statistically significant. If it doesn't include 0, then you can say that it's statistically significant and it is going to have an impact on that y variable. Okay. Any other questions before I keep moving here? I don't know why I included this small sample stuff. There's probably some reasons we'll kind of get into. Maybe if we have time, we'll revisit this on Tuesday. Just looking at, for the sake of time, I want to make a point for something else I know is going to show up. So I'm just going to copy this right here. Oh, I think I'm just running this for the sake of time. I think it's a large data set. Let's see. We'll just run this. Okay. So I've got 3 different types of divisions here. So a raw powerlifting meet is you can use like very limited or no assisted devices. Wraps, they allow you to like wrap your knees and use kind of these things that help you lift more weight. And then multiply is like this even crazier amount of assisted devices, right? So that's kind of the order in which you can use like this stuff that's supposed to help you lift more weight. So if I include all of these in my regression, why does it throw out one of them? If I include all three, what do I have? Not just multiclinearity, and we'll try to talk and touch on Tuesday about imperfect multiclinearity, but here I would actually have perfect. There's only three divisions, so if I know if it's one of the first two, I automatically know it's not the third. If it's not the first two, I automatically know it's the third. They're direct functions of each other. So what do I need to do? I need to leave one of them out. So in practice, which one would it probably make the most sense to leave out here? So if I leave out the division where there's no assistive devices used, now when I can use these assistive devices, what should the coefficients on these be? Well, relative to the zero group, when I can't use anything, if I can use these assistive devices, it's likely the total weight lifted should go. So it should be, I see what? Positive coefficients? Sure enough, I do. Okay. Now here I could also ask you a question. All right, so we're gonna have to leave one of them out if we have like these multiple categorical variables that we're kind of creating into dummy variables. What if I wanted to know what's the difference in the predicted weight lifted between these multi-applied divisions and just the wrap divisions? Well, if I don't rerun, I could rerun this regression. And instead of leaving out this raw division, I could leave out what? The middle one, which was wraps. So this would tell me what? Being in the one group, so being in this multiply competition relative to what group have I now left out? The wraps division, I can expect the weight lifted would be about 100 kilograms heavier. But if I look at the old regression, let's say I didn't leave out the wraps category, but I still asked you to find the difference between the wraps and multiply categories. How could you do that? Well, the coefficients for both of those are relative to the raw division. So I can't just state to one of those coefficients. What would the difference between the two be? Well, when I'm making predictions for that y variable, what gets added in if it's in this wraps category? 33. What gets added in if it's in the multiply category? 134. So what would the difference in between those two predictions approximately be? I add 33 to one prediction. I add 134 to the other. What's the difference between those predictions? About 100. I'm getting some blank looks. It's not clear what I'm saying there. I'll write this out because you guys are scaring me a little bit. So this is where head nods, if it's really basic, like lets me know not to waste time on it, but I'm seeing some, I think, looks that give me a pause for concern. So we had all these other variables in there. If I had included this wraps and kind of this multiply, if I'm making predictions, every time I've got, so if I have my total kilograms lifted, I would have all of this. If it's a lifter who's in this wraps division, what gets added in? Beta 2 times 1, right? So let's just assume all these other variables add up to be, I don't know, 200. So we said this was like 33. So my predicted weight would be 233. What if I'm making a prediction? All the other variables are exactly the same. Remember, when we make these coefficient interpretation, it's holding everything else constant. So now it would be all the same values. So those would equal 200. But now if it's not in the wraps division, so up here, it was in the wraps division. So the multiply coefficient would get multiplied by 0, or essentially not affect my estimate. Down here, if it's in the multiply division, well, now it would be beta 2 times 0, but beta 3 times 1, which we said this was 134. So what would I get here? 334. So what's the difference in between these two? Just whatever the difference in those two groups' coefficients are. Right? So approximately 100. And then if I leave one of those out and instead include that raw category, hopefully the estimate that I now see on multiply, or actually, sorry, I left out multiply. The estimate I see on wraps, sure enough, it's 100 pounds less. So I can ask you to compare not just to that group I left out, but you can make comparisons between the other groups that you included by simply looking at the differences in their coefficients. Right? Any questions on that before we keep moving here? Right? And this is kind of similar. I jumped the gun. We don't use p-values. We can use the confidence intervals here. Got 9 minutes. So what's something else that I really want to make sure we go through? I was just throwing that in there because I think the original data set was like 10,000 observations. So it just takes a little bit longer to run. So I was just limiting it. Huh? Yeah, it just cuts down the sample size so here, I think, oh, actually, maybe, did I not download this? You can probably, never mind. You can ignore that code. The original data I had, I guess I uploaded the one where I already only had the small sample, so I didn't need to put if the small. When I was writing this, I actually had originally a huge data set, and I realized that running some of these regressions was going to take like 5 minutes because it had like over a couple 100,000 observations. So this was like every powerlifting meet in North America in the last like 20 years. So it was huge. So when I tried running it, not on my computer, but on one of these, it was just taking a long time. So I threw in that and I forgot. I actually went back and changed it so that the file I uploaded only had that smaller 10,000 sample. So it just ran a little bit quicker. Let me think. What else would be productive for us to do with 8 minutes remaining? I thought I had a height variable in here, but maybe I didn't. Looks like I didn't. So I can't do an imperfect multicollinearity one here. I'll do that in next class with an example. I wanted to go back up here. We did some of this. Okay. So I think we should be good. I just want to have some of this ready to go. I've got a couple more things I want to say before we get out of here. But you can kind of look through this file. There's more examples where we're looking at joint hypothesis testing. So even down here, I also did some stuff with some more omitted variable bias, kind of total weight lifted and age. We kind of went through one very similar with male and body weight. So it's just more examples of some of the same stuff that we covered. Tuesday, what I'm going to try to primarily do in class, and this puts a little bit of work on you. If you have time, try to look at that practice exam because I want Tuesday's class. It's not for me. I shouldn't say I don't care, right? I want you guys to do well. But if I just show up Tuesday and nobody has questions, that means I might go over things that aren't very beneficial to your grade, right? Because you might already know them. So what helps me make sure that your grades go up if you guys ask me questions, right? So try to take a look at that practice exam, even if you don't completely work through it. Maybe try to identify some problems that you're like, I don't know where the hell to begin on this one, right? Then we can start using the class time to go through those because we're probably not going to have time to cover every single question on that practice exam. So that practice exam will be like a holy grail for next week's exam. So I'll mention a couple things about the exam before I let you guys get out of here. So just before I even go into my little diatribe here to end class, is there anything off the top of someone's head that you definitely want to see problems worked through or questions that you have over some type of concept or material that we've talked about? Yeah. Yep. Okay. We'll work through another one where we do omitted variable bias. And I'll even kind of do one with numbers, not just signs. Yep. Yeah. So I'm guessing you want to look at an example where we've got imperfect multicollinearity. Yep. I'll make sure we work through some with that. So we'll kind of think about, okay. Okay. So first of all, these are good things that I'm hearing because these are the harder concepts, right? So I'm glad that those are what you want to review and you're not saying, I just want to review how to interpret the code. We should hopefully have that down. We've done a lot of that up to this point, okay? So the exam, I asked you last class and I looked at what your responses were, and then I kind of came up with a different mode of how this exam is going to look, okay? So the multiple choice portion is going to actually be the take-home portion. Now, when I say it's multiple choice or fill in the blanks, and it's going to be done through Canvas, okay? So it's going to have multiple choice questions. Now, it's good that I turned some of them into fill in the blanks because that likely means that there were multiple answers, so you can actually get partial credit. Whereas the original exam I had written, it was like multiple choice, but there was like 2 different things you had to fill in. You could have gotten 0 credit even if you got half of it right. So that should help you a little bit. Also, you're going to have your notes. I can't restrict what you do if you're taking this outside of class on Canvas. So when you sit down to take that, I'll give you 30 minutes to do that. There's 11 questions. Okay? So about 3 minutes per question. Some of them are going to be easier and probably not take you near as much time. You're going to have resources available to you. I would hope if you take it seriously, that's going to be where you can help pull up your exam grade. Okay? I'm doing this because I want the grades to be good, right? The in-class portion is going to be the original 6 short answers that I have, and each one has, I think one of them I threw on a 4th, but each one has 3 parts, so like A, B, and C. So it's kind of all the same information, but then 3 questions so that you don't have to like restart every single question, right? So you've got kind of 6 questions there, each one having kind of 3, really 3 questions, so a total of 18 questions. And like I said, there's one of them I added a 19th question, and now I'm going to get this wrong out of memory. I think there's 104 points out of 100 points possible. So you technically could get above 100%. So one of the things that I added to those short answer, it's kind of just like bonus points. It was kind of a hard question. And so I'm like, well, separate A's from the B's here. These are going to be some additional points. You could actually get some of these wrong and still get 100 out of 100, right? So that's what the exam is going to look like. To someone's question earlier, I already forgot. You will have a formula sheet in that short answer exam. You'll have it for the multiple choice take-home portion because it's going to be on Canvas, so you can always kind of open that up. But you'll have that formula sheet in front of you. So as you're studying, have that with you because like you'll be able to reference it. You'll have it in front of you in the class or in the in-class exam as well. I think that'll help get grades kind of about where I want them. And I should say, I think it'll help probably those of you who are here today. I looked at the roster. 47 people in this class. Yikes, right? So I'm expecting probably what might be true about the distribution of the exam. Well, we didn't really necessarily talk a lot about this one. I think I maybe briefly mentioned it. My guess is it's going to be pretty bimodal, right? There's going to be a big right side and a pretty big left side as well. The thing in the middle might not be there as much. So for those of you who have been putting time in, kind of showing up, I think seeing this stuff, I just can't imagine going into this exam cold, not having seen a lot of this material. It's not going to probably go well for a lot of people who are doing that. So, but I'm talking to the wrong group. So that's what it's going to look like. We'll still do a review of those questions, specifically these topics on Tuesday. Other than that, that third problem set due before we meet in class on Tuesday, and I'll get that kind of quiz 3 kind of updated on Canvas to kind of just be one quiz. All right. See you guys on Tuesday.